All right, it's time to put some things together. So far, we've done parametric equations, and we've worked with our trig ratios. So now we're going to apply those two together to look at our projectile motion. And we've kind of slightly looked into some projectile motion, but we haven't paid attention to any angles yet. So that's what we want to do today. And we've dealt a little bit with gravity so far. We've more so looked at this equation down here. Well, this negative half g represents the A, which we've been doing. And the A, all we've known so far is that A, when it's in meters, we've been using negative 4.9, and when it's in feet, the A represents negative 16. Well, the A is just half of what the gravity's acceleration is. So, for example, for meters on Earth, gravity's acceleration is 9.8. It's going downwards, that's why it's negative, and we take half of it to get negative 4.9. That's where that A comes into play. So that's why we just simply use this equation right here and don't really worry about that negative half g. We just jump right to that. Same thing with feet. The acceleration of gravity is technically 32 feet per second squared. It's going downwards, so it's negative, and we always take half of it for our projectile motion, which in this case we get negative 16. Okay, and those are the two predominantly ones we're going to deal with, so we should try to memorize those, negative 4.9, negative 16. If it deals with centimeters or inches, I'll help you with that, but we should be able to get those down at least. And so how we're going to apply this is we're going to have an object, and it's going to be going up at an angle for the most part. We'll do some downwards as well. Okay, and then we're going to have a horizontal parameter, and we'll have a vertical parameter, just like that. So the new thing that's coming into play is that we're going to have an angle measure now. Okay, so our speed of the object, our velocity of the object is still going to be on this diagonal, right? Because that's where the speed is occurring. So we usually represent it as v sub 0, the 0 representing 0 time has gone by. That's like its initial speed. Okay, and depending on what this angle measure is, we'll just call this angle measure A for now. If I wanted to find what the y, like what this y would equal, the kind of the vertical component, how would I solve for that? Well, I know that the y is opposite angle A, and if I know the initial velocity, this is the hypotenuse up here. So to solve, we would take the sine, right? So I'd say sine of A equals y, the opposite, over the hypotenuse, which is the velocity, right? And if I wanted to solve it for y to get the y by itself, I would just multiply that velocity over, multiply so they cancel. So y really equals the initial velocity times sine of A. Okay? Well, if we know that, might want to. What do you think the x would be down here on the blue? Well, it'd be the same thing except we'd have cosine because this is the side adjacent. So really it's going to be the initial velocity times the cosine of A. And that's where this is going to come into play right here. So I have that triangle drawn right down here. And for our horizontal component, x, we're taking what's on the horizontal part of my triangle, except the only thing we got to do it is in terms of time, right? So I got to add that t in there for time because it's occurring, each second or each hour or each whatever you're dealing with. And then we also have to consider its initial starting point in the horizontal direction, right? And that's dealing with right here. It's initial start. So we got to consider that in the x direction and the y direction. For the y, this is where we deal with our gravitational force, right? We're kind of dealing with that parabola in essence. So this negative half g, that's just really our A, our acceleration of the gravity. Okay, so we use negative now 4.9 if it's meters or negative 16 if it's feet. And then we throw in the vertical component of our triangle that we drew. And we have to have it in terms of t, just like we did for the x parameter. And then we consider the initial starting point of our vertical direction as well. Okay, so there's a lot to that, and this will make more sense once we look at an example. All right, so let's apply what we just learned. This says a shot putter releases a shot put from the height of 1.5 meters and at an initial velocity of 15 meters per second at an angle of elevation of 35 degrees. How far away will the shot put land? So just a general sketch, you got a person who's throwing this shot put. He's got the shot put right here. and that shot put is 1.5 meters above ground, and he's throwing it up in the air, and it's coming back down, and it's landing on the ground, right? And he's throwing it at an angle of elevation of 35 degrees. So, for example, like this, its initial angle is 35 degrees, and its initial speed is 15 meters per second. So it's kind of nice to visualize that picture right there, but really, the only picture we need to consider is that triangle, with the velocity being the hypotenuse and the angle being that angle of elevation, okay? And then we can just apply what we learned right at the beginning, how we kind of came up with that triangle and our two parametric equations. So if we memorize these parametric equations like this, we're good. If we don't memorize it, that's okay. We can still come up with it by thinking about our components here as well. So if we think through it, for our x and our y, remember to get the x, this is the cosine because it's the adjacent. So really it's the cosine of 35 equals x over 15, right? Adjacent over hypotenuse. So I'd multiply by 15 on both sides. So really x is equal to 15 times the cosine of 35. And we have to take into account for each second that goes by, so that's where we include the t with it. Okay, so for our y, if we remember, now that's going to be our velocity times t, and it's the sine of 35. Okay, so we can think through that process like we did on that first slide, but hopefully we should be able to come up with, just try to draw that triangle and get those components in there. Then it's helpful when we try to write our parametric equation. So for our x parameter is just basically our horizontal part of our triangle. So velocity, the initial velocity, times the time, times cosine of 35. But then we also have to consider its initial starting point horizontally. Well, if I look at this guy, it was only up 1.5, so that's in the y direction. That's the initial y. So I don't have anything here for an initial start in the x direction. So it's just really plus 0, or I don't even have to worry about it. And then for the y, this is where our gravity comes into play. So I can't just simply put this in there. That's a part of it, right? That's basically our first degree part of it for the t. But we also have to consider the gravity. So it's meters, so that means I'm using negative 4.9 for gravity because it's really negative 9.8 and half of that, so negative 4.9 t squared. And now we put in our first degree part. That goes in the next part. So we'd say plus 15t cosine of 35. And then we throw on our initial height of 1.5, right? 1.5 meters, that initial height. All right, so now we got to decide, what am I trying to find? I want to find how far away the shot put will land. So how far away? So really that would apply to this equation. But I have to know what the time is when it hits the ground right here. Well, what do I know about the ground? Its y would be 0, right? So I need to plug in 0 for y into my vertical component here, and I need to solve for t. So there's a few different ways we can solve for t here. It's a quadratic, so one thing I could do is the quadratic equation. Another thing we could do is take our calculator, make sure it's in function mode, which it is, and degree mode, which it is, and we could graph our parabola and find its roots. And instead of t, remember we got to use our x because we don't put t's for this guy when it's in function notation. So our x is representing the time, and then 15t times the sine of 35. And I might just go zoom standard to start, although I might have to adjust this. So zoom standard fitted on there, and all I want to do is find this root right here where it hits the ground. So I'm going to hit second calc, find the 0, and this will find the time when it hits the ground. So left bound, go left of the root, right bound, go right of the root, take a guess, and there we go, 1.9, about 1.9 seconds, I guess. I should probably be as exact as I can, so maybe I'll write quite a bit of this out. 9156473. And then what do we do with that number? Yeah, we plug that number in for time of our x parameter. And we end up with about 23.5 meters right there. Okay, so the biggest thing is make sure you draw your triangle, write your parametric equations, and then start deciding what do I need to plug in. Should I use the quadratic formula? Can I graph it and look for the roots? Things like that. Okay, because every situation is going to be a little bit different. For example, here, this says, suppose a baseball player hits a ball with initial velocity of 125 feet per second at an angle of 29 degrees, connecting with the ball 3 feet above the ground. Will the ball clear the 20-foot fence, which is 350 feet from home base? Okay, so some of you might even like to draw a little picture right off the bat. So you got your little baseball player here, and he's swinging a bat, and he hits a ball, and he's trying to see if it clears this 20-foot fence. So his ball is going up, and it's coming down, and we're trying to see, is it going to clear that fence right there? And he hits it, 3 feet above the ground? So 3 feet above the ground. And from home plate to the fence, that is 350 feet. So sometimes that's good to visualize, but really the ball's not going to hit the ground until after the fence if it clears that wall, that fence. Okay, so let's start by drawing our triangle and put in the information we know. Well, we know he's hitting it at 29 degrees, and the initial velocity is 125 feet per second. Okay, and then we use our parameters. So the x parameter, remember, is the initial velocity times the time times cosine, because it's right next to the angle. So we'll say 125t cosine of 29. And remember, we consider its initial distance horizontally. Is there any initial distance horizontally? There is not, right? Because this is basically like when x is 0 right here. Okay, so we don't consider any initial horizontal. What about the y? Well, we consider our gravity. It's in feet. So now we're using negative 16, right? Because gravity is negative 32. We cut it in half, so negative 16t squared. And then we put our horizontal, our vertical component, velocity times time times the sine of 29. So that piece will go right here, 125t times the sine of 29. And it's at an initial height of 3 feet off the ground. All right, so now do I do the same thing? Do I just plug in when y is 0? Is that going to help me out? Well, y is 0 is right here. That's really not going to help me. So what do I need to do? What do I need to plug in? Well, I need to plug in when y is what? I want to plug in when y is 20. Okay, I want to plug in, what I'm concerned with is where is that ball at when it's 20 feet above the ground? So I'm going to plug in 20 for y here, and it's a quadratic, so I need it equal to 0 in order to solve it, so I'm going to subtract this 20 over. So really we just get 0 here, and this is going to become negative 17. And technically I still could use my calculator and graph it and find the roots with this new equation, or I could use the quadratic formula. The quadratic formula would be pretty nasty, right? Because my a would be negative 16, that's nice and easy. My c would be negative 17, that's nice and easy. But my b would be 125 sine of 29. So that's pretty gross. So I might just want to graph this again, even though it won't be the graph of my actual like baseball where it's hitting the ground. Where it'll hit the ground is at the top of the fence, if that makes sense. So we're looking for that root right there to find the time that'll take the ball to be 20 feet in the air. Remember, if it doesn't show up on your graph, take a look at your x. Right now I'm at 2.5, which is about right here, so it's not hitting my graph yet, so I got to keep going to the right until it shows up. There it is. So left bound, I hit enter because I'm left in the x, right, of my root, and now I'm right of the x in my root, and then take a guess. And there we go. So about 3.4824762. So I'm going to write that whole thing down. So remember, that's when the ball is 20 feet in the air. It's 3.4824762. And then what do we need to do? We need to plug that into the time of our horizontal component, our horizontal parameter, and figure out if it's going to be bigger than 350 feet. Because if it is, then I know it'll clear it. So that's what I'm going to do. And I'm going to use that entire time. I'm not going to round it at all because I want to be exact. Yeah, so that ball's going to be 20 feet high on its way down at 380 feet. So really this ball is going to get up here and it's going to clear it right here. So this point is really 2380. Okay, so it'll definitely clear the fence. So yes, it will. Okay, so that one it took a little bit extra work. Instead of just being able to plug in 0 right away, I had to plug in 20 for y because I wasn't looking for when it hit the ground. So you just have to be careful with some of those situations. But like I said, the biggest thing we're concerned about is drawing that triangle to help you out to be able to write your parametric equations. And then you can kind of think through on what numbers you need to plug in and how to solve. And using that calculator, graphing and finding the roots is probably the easiest way when you get it equal to 0.